people might want to again go to slides.
Actually, I kept reading how instantons can mean something about like the end of the universe randomly.
What?
Be a little about how instantons can end the universe randomly at like with no given warning. So I was wondering if
Oh, okay.
you had any opinion on that.
Well, you know, at least you see how instantons can be used for that purpose. And whether the universe would come to an end is a separate question. But anyway, at least you see the role of instanton there. All right, so let me get started. So this is really the very last discussion section. And all that's left is the homework. And as I said, I'm going to talk about magnetic monopole and strong CP problem and axion related to instantons. And I am writing the solution set right now, so I believe that will be ready tomorrow. And make sure that you do fill out teaching evaluation. I really need that. Okay? So magnetic monopoles. So as I advertised in the morning, so magnetic monopole is something Dirac put in by hand and studied this topological nature of it. But that magnetic monopole actually can come out as a prediction of certain gauge theories. And that's the aspect we haven't talked about. So that's why I'd like to mention it. So magnetic monopole is actually a kind of topological defect in that sense. So to make the story very concrete, I talk about the example based on SO3 gauge theory. And as you know, SO3 and SU2 are the same thing. So you can view this SU2 gauge theory as well. But the reason I'm saying this is SO3 is that the Higgs I introduced to break the symmetry is in a vector representation of SO3. So that's a J equal 1 representation. So it's a triplet of the three components in it. And if one of the components acquires a expectation value, then you have one component that's a VEV, two other components are still zero. So you still have the freedom of rotating the two other components. So SO2 symmetry is still unbroken. And we have looked at this example already many times over. SON can be broken to SON minus 1 in general by saying one of the components have a VEV. And so this is just one example of that. But the point here is that the unbroken SO2 symmetry, two-dimensional rotation, is also the same thing as U1 because it can be parameterized by one angle. So you can actually write it also in terms of the phase. And we can identify this unbroken SO2 as electromagnetism. So we have a theory which is a non-Abelian gauge theory based on SO3 or SU2 group, whichever you like, but it's broken down into an U1 at the end of the day, which we identify with electromagnetism. And the manifold of the ground states is basically that this triplet of the Higgs has a fixed the modulus.
God.
I'm sorry? Somebody said something?
Oh, whoops.
Yeah, I'm hearing some noise actually. Oh, it's gone now. All right. So the vacuum manifold is that you have this triplet of Higgs with a fixed modulus or absolute value of it, so length. So that defines a two-dimensional sphere. So that's the vacuum manifold. And the topologically non-trivial thing here is that if you look at the three-dimensional space, then infinity of three-dimensional space is two-dimensional sphere, surface of two-dimensional sphere. And then you're talking about the map from that two-dimensional sphere, which is the infinity of space, onto the manifold of the ground states, which is also S2 in this case. And that's why you can talk about this winding number of the infinity of space mapped into the space of the possible ground states of this Higgs system, and hence you have this winding number. So that's how you can have these topological defects. Okay, any questions about this setup? All right, so then the configuration looks something like this. And so the boundary condition we set up is that this phi I, which is the triplet of Higgs, now orients along the direction of the towards the infinity. So Ri is x, y, and z. So if you go to the infinity in positive x direction, then you're turning on the x component of phi. Along y direction, y component phi, z direction, z component y, and in between, that's the linear combinations of them. So the phi, the field, is pointing in the direction of space. And that's why the picture would look something like this. And this kind of the configuration is often called a hedgehog because it kind of looks like a hedgehog, right? And so that's the boundary condition. And so this boundary condition achieves what I just said on the previous slide, namely that phi forms two-dimensional sphere because its length as a vector is fixed by the potential. And that is now mapped onto from the two-dimensional space at infinity in a way that they're in one-to-one correspondence. So that has the winding number, in this case, winding number 1. So that's the boundary condition. Now we have to actually extend it to fill in the entire three-dimensional space. So here's the ansatz. So taking this boundary condition, so this is the asymptotic limit r going to infinity, and at the origin, as we have seen in many other example topological defects, symmetry is restored. So we take phi I to be 0 at the origin, using this function f of r, which vanishes at the origin. But this f of r goes to 1 at the spatial infinity, so that would asymptote to this boundary condition I mentioned earlier. So that's the ansatz. And of course, we need to come up with a gauge field configuration too. So SU2 gauge field comes with the 3 components because there are 3 generators, and that's the generator A here. And the point of this kind of discussion here is that you are sort of mixing up the gauge index I to spatial index I. So in the same way, the gauge field now has 2 indices, the spatial index I, for which component of the vector you're looking at, and the index A, which refers to which generator you're looking at. And you mix them up with the spatial indices, so that's why I end up with this funny symbol, epsilon IAB. And so I direction of the component of the vector potential A for the generator A turns out to be proportional to the spatial direction B. So that's this funny combination epsilon IAB. And once again, there is the function g of r which we need to fix in order to solve the equation of motion. But having set it up this way, you can identify what the magnetic field is for the unbroken U1, which is given by this formula. So you basically project this non-abelian magnetic field, which has 2 indices, together with phi A to select a component which is chosen by the symmetry breaking. And further, you add that together with the radial direction Ri to identify the radial component of the magnetic field. So at the end of the day, this is the question whether this BR really has the kind of form expected for the magnetic monopole. So anyway, that's what we're trying to do. Any questions about this? All right. And that's what is called Polyakov monopole, because the Harold Toft and Andrei Polyakov are the first people who came up with this kind of a solution. So this is what we have to do and solve the equation of motion numerically. It turns out, though, that in special case, when the scalar potential is totally flat, you still need to keep the expectation value fixed. But you take the limit that the steepness of the potential goes to just 0, it's totally flat. That is a limit called the BPS limit. So in this limit, you can actually solve for the solution analytically. Now, otherwise, you have to do it numerically, but in this case, you can do it analytically. And so I'm plotting the solutions for this case. So the phi indeed starts with 0 and turns on, and asymptotes to the limit where the boundary condition is specified. So that's what is expected. The gauge field A also turns on, but eventually goes down to 0. So that at spatial infinity, then the covariant derivative ends up being 0. And the interesting thing is this R squared times B. So B is the magnetic field. And if you have a magnetic monopole, then the magnetic field should go down like 1 over R squared, as you expect from Coulomb's law. So that's why I multiplied R squared on top of it. And indeed, what you see here is that R squared times B asymptotes to a constant. So that is really a demonstration that you're looking at actually a magnetic monopole solution out of the gauge theory. And the fact that this actually asymptotes to 1 means that this corresponds to magnetic charge 1 in the unit where E is 1. What we also know is that this can be viewed as SU2 gauge theory. And if you introduce matter field in doublet representation of SU2, then if you break it down to U1, then each component has electric charges plus 1/2 E or negative 1/2 E. And now you can check if Dirac's quantization condition is satisfied, and it is, because the magnetic charge is 1, minimum electric charge is plus minus 1, so their product is plus minus 1/2. And that's exactly what we derived earlier as the Dirac's the quantization condition. So in this case, what you see here is the magnetic monopole is an outcome of this theory. It's not what you put in by hand. But once you do have magnetic monopole as an outcome of this theory, then you can see that Dirac's quantization condition is automatically satisfied, as it should be, because the theory we worked out consistently, and nowhere in the process, then topological quantization should be invalidated. But it's actually certainly a good thing to check that indeed the quantization condition is satisfied in the way we expected from Dirac's argument. Okay, any questions about this?
Can you remind us, like, what's the lambda issue?
Lambda is the steepness of the scalar potential. So you produce this Mexican hat potential, and the steepness is the parameter lambda. But what I'm doing here in the BPS limit is that I keep the expectation value fixed, but flatten out the potential. And that is the limit where I can write down the analytic solution.
Okay, thank you.
Okay, any other questions here?
I didn't follow why. Sorry, what theory do we get the electric charge being 1/2 from? I remember the quantization condition having an
right.
An
So remember we are talking about SO3 gauge theory, and if you start with a triplet Higgs, then the triplet decomposes into 3 components, obviously, because of the 3 components to start with, and they correspond to charge +1, 0, and -1.
Mm-hmm.
But if you have a matter field in a doublet, then you have only 2 components, and every generator, of course, is traceless. So the only possibility is that the electric charges are +1/2 and -1/2. Right?
Okay. So this is okay. So this is still the same gauge group, but a different matter.
Right.
Okay.
So the smallest non-zero electrical charge any particle can have is 1/2, while the magnetic charge is 1, so that their product is 1/2, which satisfies the Dirac quantization condition.
Okay.
Okay. All right. And as I have already shown in the morning, and this kind of magnetic monopole solution can also arise in condensed matter systems. So this pneumatic liquid crystal is one example of such a system. And you can have this kind of, similar to hedgehog we have seen on a previous slide, given by this alignment of these liquid crystals along the radial direction. Or if you have this kind of hexagonal shape array, then when these the hexagons actually meet, that would also have this radial lineup of the liquid crystals. So that's also a magnetic monopole solution. So you can have this kind of topological defects indeed in liquid crystals, and so the mathematics is exactly the same. We have 2-dimensional infinity, which is S2. And the liquid crystals can also orient in every direction. That forms S2, and that's the map from the spatial infinity to the space of orientation of the liquid crystals. And then you are still using the same math, namely pi2 of S2, giving you the winding number for non-trivial solutions like this. All right, so that's all I wanted to say about topological defects. Any questions about everything? Okay, then let me move into what is called the strong CP problem in the strong interaction QCD, and Axion as a potential solution to this. So this actually doesn't have to be QCD here. In any Mills theory, And let's forget about the matter fields for now. And Yang-Mills Hamiltonian is basically E squared plus B squared, just like electromagnetism. And let's say that you take the wire gauge, as typo is not tape, it's take or wire gauge, that the time component of the gauge field vanishes. And we're also looking for static solution, which means that the electric field now vanishes. So then the only thing you need to do to minimize the Hamiltonian, just like we always did with the scalar field theory, looking for the minimum of the classical theory to begin with, is to find a solution where magnetic field vanishes. And what that means is that we want the magnetic field to be pure gauge so that the field strength automatically vanishes. But now you know that pure gauge condition is that the U is a map from three-dimensional space into the group. And to the extent that we are looking for the finite energy configurations, every direction you go to the infinity, you always make sure that the field strength would vanish in every direction you go. So in some sense, you can identify every direction of three-dimensional space. Then you can consider three-dimensional space to be three-dimensional sphere. So infinity will correspond to South Pole, right? And then you're talking about the map from three-dimensional sphere into the gauge group. And it turns out that the pi 3 of any simple compact Lie groups has a winding number. So you can classify the ground state of this Yang-Mills theory according to these winding numbers. And winding number, of course, can be any integer. So you can have a basically potential energy like this picture here. For every winding number, integer, you find a pure gauge configuration like this one, and therefore energy vanishes. In between 0 and 1, and there's no well-defined winding number. So what you can consider this number to be, then is a Chern-Simons term. And when you specialize Chern-Simons term to the case of the pure gauge, then that precisely corresponds to the winding number. And we looked at that actually last week. So you can regard this horizontal axis to be the Chern-Simons number, which is the function of the gauge field A. And when the gauge field happens to be pure gauge, given by the winding number, you have zero energy. So this is the kind of the potential energy you should have in your mind as a potential energy for the Yang-Mills theory. So now the situation is, unlike the electromagnetism we are familiar with, you have infinite number of ground states. And then you have to ask the question, can you tunnel from one ground state to another? Because you have an infinite number of them. And the answer turns out to be yes. And the way you see that turns out to be what's related to instanton. And once you actually do tunnel, then it turns out that would define what is called the vacuum angle, namely the strong CP problem now arises. And then we get into the discussion of axion as a way of solving it. So this is the beginning of the whole story here. So any questions about this?
So I didn't. Sorry, I thought we were thinking about like the right homotopy map to, or homotopy map index to look at as being defined by the boundary of the space. Why are we now taking all of R3 to S3 instead of S2?
Yeah, so what we want is that we're looking at this finite energy configuration. And in particular, of course, we're looking for ground states at zero energy. And to make sure that the energy is finite, then these field strengths have the fast enough towards the spatial infinity. So every direction, the fields go to zero at the end of the day. So every direction happens to be the same. So that's why we can consider them to be the same point, namely the south pole of the three-dimensional sphere. And I think what you're saying is that when we discuss topological defects, we kept the infinity of space to be S2 instead.
Yeah.
But that S2 was actually something that can be transformed, the gauge transformation to a identity. So we had this hedgehog ansatz for the magnetic monopole, for instance, and you have this, the field sort of sticking out towards the infinity, but they are all the same under gauge transformation. And that's what we have done with the gluing the two hemispheres together in the case of Dirac magnetic monopole. So in some sense, the spatial infinity in this case is where the Dirac string is. But when you perform a gauge transformation, you can make it actually trivial. so that you can cover it up with the South Pole. So either way, you can regard the whole setup to be S3 as a three-dimensional sphere. So there's actually no difference between them. Does that answer your question, Max?
I'm still confused, unfortunately. So wait, maybe maybe it would be helpful to understand how S3, how you can think about the monopole case is just being on S3.
So in the case of the first discussion of magnetic monopole, we consider S2 around the magnetic monopole. And then we discovered that the gauge field looks singular, either at the North Pole or South Pole. And then we figured that you have to actually glue two hemispheres together using gauge transformation at the equator. Right? So it turns out that what you have to do in the case of this Toft-Polikov monopole is that at spatial infinity, which is S2, it looks like this is very non-trivial. But you can actually do a gauge transformation to make every direction to point the same direction in the gauge space, phi I, and then glue that together to the other hemisphere, which corresponds to South Pole. So at the end of the day, even though I'm talking about spatial infinities S2, that S2 is what corresponds to the equator in the previous example. You perform gauge transformation on that S2 and make it trivial so that it can match on to the southern hemisphere without any singularity.
Okay. Okay. Yep.
So anyway, so back to the Young-Mills theory, we can classify different ground states using this winding number. And the question is about tunneling among them. And here I need to do a little detour to introduce tunneling in the field theory context. And that actually turns out to be what is called the instanton. So let's look at the example of quantum mechanics first in a double well potential. This is the point particle of the Lagrangian here. And then the point particle is living in this double well potential. And if the particle is sitting in one of the minima, we know in the quantum mechanics problem, it can tunnel to the other minimum too. And the way you actually look at this problem from the path integral point of view is to first go to Euclidean theory, so that you flip the sign of the kinetic term with the IT, right? And then you look at the Euclidean equation of motion. And so because what happens here is that relative sign between kinetic term and potential term flips, going to the Minkowski space is the same thing as flipping the potential around. So it's now upside down potential. And using this upside down potential, you solve the equation of motion. Then you find a solution to that. So if the particle starts at this the left minimum, then in the original potential, classically, there is no solution that rises up the potential, come back down, and that's why tunneling is not a classical physics. It has to be quantum physics. But if you flip the potential upside down, then you do find a classical solution where a particle is sitting at this local maximum, and it slowly starts to roll down the hill, and then starts to speed up, then whoop, and goes to the other top of the hill. And that is given by this tangent function. And it's no coincidence that this is exactly the same form as we have seen for the domain wall solution, because for the domain wall solution, we are dealing with space. So that's a Euclidean theory to begin with, and hence the same solution. So it turns out that if you actually flip it around, go to Minkowski space, Euclidean space, tunneling can be described in terms of the classical solution to the equation of motion. And it turns out that if you actually plug this solution back into the action, then you find the WKB formula. So here is the Euclidean action. So just by plugging in the solution we have found on the previous slide, then you just put that into the classical action. You can just compute the integral of this Lagrangian in Euclidean space, and you find this expression in 4m lambda over 3g squared. On the other hand, if you do the WKB formula, which you have seen in quantum mechanics class, and specifically for the case of energy 0, because that's where it's sitting here, then all you have to do is to compute the square root of 2m times v and integrate it from one minimum to the other. And then you find the same result, 4m lambda over 3g squared. And this is not a coincidence. You can prove that the WKB formula really does correspond to the Euclidean action following the classical solution to the equation motion, but equation motion for the Euclidean space instead of Minkowski space. And this is what you call the instanton, because the solution you have found is that sitting at the local maximum for a while, then slowly starts to go down the hill and zoom, go up to the other hill. So solution is kind of interesting only for limited time interval. So solution is there only for an instant, and hence instanton. So the word instanton refers to this classical solution to the Euclidean equation of motion, which interpolates two minima in the Minkowski theory. And the way you interpolate between the two would be a solution that exists only for a certain time interval, and hence instanton. So that's the connection between tunneling and the instanton. Okay, so I stop here. Any questions about these two slides? Have you guys seen this somewhere else?
String theory.
Oh, in string theory class, okay. Of course, not everybody takes string theory class, but anyway. All right, so that's how you find the instanton. So the lesson out of this example is that suppose you are looking at some tunneling question. Well, what you have to do then is to first switch to the Euclidean theory and look for the solution of the equation of motion in the Euclidean theory that interpolates different minima of the Minkowski theory. And that's exactly what we do for the Yang-Mills theory too. So once you go to the Euclidean theory, then your action is positive definite. So the E squared minus B squared is now E squared plus B squared, so that's positive definite, semi-definite. And then you can actually play the following trick. I can write F and F dual, that's epsilon mu nu rho sigma F rho sigma over 2. So the going from F to F twiddle really switches E and B fields around. So that's what is called the dual. And the F squared then can be written as trace of F minus F twiddle squared plus 2 FF twiddle. So let me do this slowly. So the F squared is what you wanted. F twiddle squared, because all this twiddle does is switch E squared, E and B around. F twiddle squared is B squared plus E squared, which is the same thing as E squared plus B squared. So F twiddle squared is the same thing as F squared. And the cross term is minus 2 FF twiddle, which is canceled by the last term. So the only change is the factor of 2. But having done this, you notice that this F minus F twiddle squared is also positive semi-definite. So it's 0 or above. On the other hand, this trace FF twiddle is nothing but this Chern character, which has this topologically quantized to an integer. So once you specify a class of the gauge theory which correspond to a particular the winding number, then this is just a number, integer, times the coupling constant factor up front. So what you can prove this in a very simple way is that Euclidean action is bounded from below, and the minimum is specified by this topological number. And in particular, once you have this lower limit on the Euclidean action, lower limit is achieved when this F minus F twiddle vanishes. Namely, what you're looking for is a field configuration where F and F twiddle are the same. And this condition is called self-dual, because taking dual, putting twiddle on it, doesn't change it, and therefore it's self-dual. And so this is actually the equation of motion you're supposed to solve. So once you find a field configuration which satisfies this self-duality condition, that F is same as F dual, then this argument tells you that that field configuration is automatically a solution to the Euclidean equation of motion. And in addition, because this configuration has this non-zero topological invariant, we know this topological invariant interpolates from one winding number to another winding number, we studied this in the 1+1 dimensional QED in great detail. We also had an argument why that is also true in 3+1 dimensions. So this topological invariant is nothing but the interpolation of one winding number to another. So what we are doing is basically, again, flip this potential around. You start with 0, say, then it starts to roll down the hill, then quickly zoom back up to the winding number 1. And that's the solution given by this self-dual field, which you can actually write down explicitly, as you'll see on the next slide. So any questions about this idea? I'm just using the same idea we had for the double wall potential in quantum mechanics, now applied to the gauge theory.
So these are solutions that interpolate between two pure gauge equations, right?
That's right.
Okay.
So the fact that such a solution exists already tells us that you can find a tunneling from one winding number ground state to another winding number ground state. Any other questions? All right. So here we go. This is actually explicit form of the solution, which doesn't look too complicated. You have to accept some few new notations about this. So sigma mu and sigma mu bar are basically Pauli matrices, except that you also need the fourth component, which happens to be identity matrix times I or minus I, depending on which one you're looking at. And then we take this combination of the antisymmetric product of the two, sigma bar mu nu, and you put that in here. And once again, you see this strange mixing between spatial coordinates and gauge coordinates, because sigma mu nu is meant to be some kind of gamma matrices, right? But you're using these gamma matrices as a way of describing the generator for the gauge field now, because that's what A mu is. So you have this funny mixing between the spatial indices and gauge indices going on. But the point here is that when you take this vector potential and compute the field strength as a whole is proportional to sigma bar mu nu. And you can work out that sigma bar mu nu is actually self-dual. And that's easy to show. If you take sigma 1, 2 element, then it's tau 1, tau 2, so that's tau 3, right? But if you also take 3, 4 element, and 4 is identity matrix, so it's also proportional to tau 3. So sigma bar 1, 2 and sigma bar 3, 4 are the same. So that's why this F mu is self-dual. And once you know that this is self-dual, then you know that this is a solution to the equation of motion. And because it's self-dual, also that you know what the action is without computing anything. So the action turns out to be 8 pi squared over g squared. So you can work out that this solution indeed does interpolate between one winding number to another. The solution has some parameters in it. X naught is basically the center of the solution. And rho is how much spread out this solution is. So this is sort of size of an instanton. And no matter where the center is, no matter what the size is, this is a solution of the equation of motion. So this solution now interpolates between two different winding numbers. And so the e to the minus action is a WKB formula for the tunneling amplitude. So e to the minus 8 pi squared over g squared. And at the end of the day, we know that Yang-Mills theory becomes strongly coupled at long distances. So G actually becomes very large at the end of the day. So this exponential suppression is not much of a suppression at the end of the day. So this kind of tunneling actually becomes unsuppressed. So at the end of the day, the instanton turns out to be a very important effect, giving you this the tunneling among all these different vacua in this Yang-Mills theory. Okay, any questions about this? All right, so now that we know there is the tunneling going on, then you have to ask the question, what is then the eigenstate of the Hamiltonian? And that's something actually you know from condensed matter physics, namely that the potential we are talking about here is periodic, because moving one unit is supposed to be gauge transformation. So energy doesn't change in the gauge transformation. Therefore, we know the potential is periodic. And when you're looking for the wave function in periodic potential, then you know the answer is plain wave-like solution. It's called the Bloch's theorem in the condensed matter physics language. And so what you find is that this kind of the linear combination, which is plane wave-like because it goes like this, like e to the IPx, where x corresponds to n, p corresponds to theta. So this is what is supposed to become the eigenstate of the Hamiltonian. And so this is actually going through this tunneling from one state to another. So you sum them up in a way that this is now become an eigenstate under tunneling phenomenon. So each time you tunnel and increase n, then you change this phase by 1 power of theta. So that is an eigenstate of the tunneling process, hence becomes the eigenstate of the Hamiltonian. And assuming this simple potential, which is also an approximation, that then this is actually also supposed to become this kind of cosine form. And this theta now reveals the eigenstate of the Hamiltonian you're looking at. And this angle theta is what we call the vacuum angle. So it was not there in the original theory when you look at the Lagrangian, but it turns out that ground state needs to know which theta you are looking at. And therefore, theory is not specified unless you also specify this vacuum angle. And you may say, okay, but you can always fall down to 0, but you can't because there is no term in this Lagrangian which can change theta. So once you're sitting here on the slope, you sit there forever. So vacuum angle theta is not something you can change. So in Yang-Mills theory, this vacuum angle theta becomes a fundamental constant of nature. It's like coupling constant or mass of the electron. That's not something you can change anymore. It turns out that you can also do a similar exercise in 1 plus 1 dimensional QED. That's a U1 theory, which looks like a really trivial theory of the free photon without any degrees of freedom. But it turns out that 1 plus 1 dimensional QED also has a vacuum angle, which is actually described in more detail in the lecture notes. So to spare time, please look at that. So anyway, this is the basic message here. Yang-Mills theory has no additional parameter in the Lagrangian except for the coupling constant. But it turns out that there is this hidden variable, which is fundamental constant of nature, which is called the vacuum angle. Okay, any questions about this? This is kind of confusing point, I'm sure.
So the vacuum angle is like a relative phase between all the different winding numbers.
Mm-hmm. Okay. That's right. So that's actually defined in by this formula here when you build up this theta vacuum. Okay, so that's the vacuum angle. And once you have the finite theta, then you actually have a problem if you apply to this QCD, because having non-zero theta actually ends up predicting that it leads to an electric dipole moment of a neutron. So this term can be actually now put into the Lagrangian by the following trick. So we now have this the theta vacuum. And remember, this n is basically the eigenvalue of the Chern-Simons term. So you can then absorb this theta by taking a new convention on defining what this n vacuum is, by applying a phase rotation, the convention of the phase changes of the wave functions given by the Chern-Simons term. You do that both for the initial and final states. So then you find that your Lagrangian is modified by the total derivative, or basically changing the Chern-Simons term from the negative infinity to positive infinity. And we know that the change in Chern-Simons term is nothing but the integral of this FF dual, the topological invariant. So instead of assigning this phase on the state, you can put that into the Lagrangian. And that looks actually more tractable, because now you're looking at the theta angle to be a Lagrangian parameter, then you know what to do with it. So now that you have this new Lagrangian, which has theta parameter in it, you can ask the question what symmetry it breaks, and it turns out it breaks CP symmetry. And it also breaks the time reversal symmetry, which is easy to see because FF dual, as I said, is E dot B. And under time reversal, E doesn't change, but B does. So under time reversal, theta goes to minus theta. So having a definite theta violates the time reversal. And that's why electric dipole moment can be induced from theta parameter, because electric dipole moment is a coupling between the spin and electric field. And under time reversal, electric field doesn't change, but spin does. And therefore, this Hamiltonian is odd under time reversal. Then such a thing can be induced only in a theory that violates time reversal, but theta parameter does. So you do expect that to be induced. And again, in lecture notes, I try to give you a better idea on how this can be computed at the end of the day. But anyway, so that you see already that neutron electric dipole moment can be non-zero once you have this theta angle. And that actually turns out to be briefly explained here. So it turns out that when one of the quark masses vanishes, then you have a massless fermion. A massless fermion can be chiral rotated, but chiral rotation changes the gives the Jacobian from the measure, and Jacobian coming from the measure turns out to be precisely a fifth dual term, which can allow you to change theta freely. So when you have massless fermion, then theta parameter actually does become unphysical. But as I have shown you also earlier, in experimental data, all of the quark masses seem to be non-zero. So you cannot change theta arbitrarily, and therefore theta parameter is a physical parameter. But nonetheless, the impact of theta parameter has to vanish when you send even just one of the quark masses to zero. So that gives you basically this idea that you write an expression that vanishes when one of the quark masses goes to zero. At the same time, you can have a stable limit when you send one of the quark masses to infinity, because that's when you just decouple one quark species. And to satisfy both requirements, it turns out that this is the unique solution, in a way symmetrical among three quark flavors. So this is how you can actually estimate it. And the rest is dimensional analysis, because the strong effect comes only from the QCD scale lambda. And everything has to be proportional sine theta because T violating. So if you put all of these together, you can get a pretty good estimate on what the electric dipole moment should be. And the answer is about 10 to the minus 16 e centimeter times sine theta. But experimental limit is actually 10 to the minus 26 e centimeter, which then tells you that theta has to be less than 10 to the minus 10. And that's what is called a strong CP problem, because the theta parameter was just an angle, which it was of the order of pi, naturally. But somehow this angle has to be a small 10 to the minus 10th. It didn't have to be like this, but the data requires that. So that's when you start to feeling nervous that we are missing something. So that's the strong CP problem. So any questions about this?
Nervous in the sense that there could be like another symmetry that's suppressing it?
That's right. So that's what you would ideally would like to see. And just to tell you how incredible this experimental limit is, suppose you blow up the size of the neutron to our planet, and electric dipole moment means that there's a displacement among the charges, and the amount of displacement you can have after blowing up the size of the planet is about a few microns. It's an incredibly strong experimental limit. And so you have to satisfy that limit. So why is this angle, which can be anything, has to be so small? Why you are supposed to be here, where this red arrow is pointing to? So that's where people try to explain this by making this theta parameter, which was just a natural constant, but replace it by actually dynamical field. So what you do is to introduce a massless field called axion, but this axion couples to a fifth dual in a way that's similar to theta. And because A has mass dimension 1, this coupling needs to have one mass dimension downstairs. This is a non-renormalizable coupling, but we know how to generate it when you integrate heavy fields. So this theta plus A over FA now acts as a parameter. But because A is dynamical field, then it can actually roll down this potential and settle where the CP violation disappears. So that's this very simple idea. And in order to work out consequences, you have to be a little bit clever, because this is after all a confining theory. Then you have to switch to the chiral Lagrangian, then make sure that everything works out from this. And I don't seem to have time to explain all these details, but that's something, again, I explain in the lecture notes, so please look at that. So at the end of the day, you can compute the mass of the axion. And typically, people take this axion decay constant, Fa, to be a very big number, like 10 to the 12 GeV. Then you find the axion mass to be something like of the order of microelectron volt. It's a very light particle. And it turns out that for this kind of mass, it becomes a good dark matter candidate of the universe. And that's why there's so much attention to axion these days. So axion can double up to play the role of explaining why theta angle in QCD appears so small to solve the strong CP problem. But also the axion itself can become dark matter candidate. And if you're talking about such a light particle, light boson, then the dark matter density is fixed, but the mass of the axion is so small, so number density has to be huge. So what you're talking about is actually a Bose-Einstein condensate of this axion particle, which, as you have learned already, can be described in terms of the classical scalar field swashing back and forth in a quadratic potential. So that's how we actually end up describing this Bose-Einstein condensate of the axions working as a dark matter of the universe today. So that's the connection between the strong CP problem to this instanton we talked about as a Euclidean solution, which then ends up giving us this massive field, which comes from the instanton effect, which ends up being an interesting number for the purpose of cosmology. And there are all kinds of constraints coming from astrophysicals limit, accelerator limits, collider limits, and so on and so forth. But as I said, there is this range where it can serve as a dark matter as a function of this axion decay constant Fa. So 10 to the 12 GeV is this range I talked about. And the idea is that this axion potential has such a small mass, which means the potential is so shallow that at the beginning of the universe, when energy density was so high after Big Bang, then this looks totally flat. So axion could have been anywhere in this potential because no way to tell where the minimum is in the early universe. So presumably, axion was sitting somewhere on the potential, which may not be at the minimum, which is called misalignment. But once the universe cools, and once the total energy density becomes comparable to this height of this potential, then axion all of a sudden realizes, oops, I'm not at the minimum. I have to go to the minimum and start to go down the hill. And then it starts to go sloshing back forth like this. And this oscillating motion of the scalar field, as I said, is actually Bose-Einstein condensate. So it behaves like matter. You can solve this equation of motion numerically. And this red line is what you would expect for the behavior for the cold matter. This blue wiggly line is what you can solve for as the equation of motion for the scalar field. And at the later stages, you can see that this red line is a perfect envelope to this oscillating scalar field. So it really does start to behave like matter. So the Bose-Einstein condensate of this light scalar field then does behave like matter, which has very small coupling to the standard model and therefore dark matter. And that's why it can become a candidate for dark matter at the end of the day from this mechanism called misalignment production. So that's what I want to tell you about the QCD and axion. Any questions here?
Is the amount of misalignment you would need to explain the observed dark matter?
Yeah, so that's an excellent question. So misalignment mechanism has this ambiguity that you don't really know what this initial misalignment was. So you can make an order of magnitude estimate, given this potential goes all the way from 1 over Fa to minus 1 over Fa. So that's of the order of the axion decay constant. So that's the dimensional analysis kind of estimate how big a misalignment is expected to be, but you don't really know. So it turns out that if you go to smaller mass, then same misalignment would give you too much of an axion. So you need to start with a smaller amplitude. And if you go to too light axion, then you end up tuning the initial condition to be already very close to the minimum. Then you also back to unnatural behavior. So you don't want to do it. But to what extent you are willing to sort of tune the initial condition is sort of subjective criteria. So, that's a matter of taste at some level. So that's an excellent question. We don't really know.
Professor, could you explain again how the theta angle ends up coupling to the neutron EDM?
Yep. So the way you can actually show this very explicitly is that you have this coupling theta in here, and forget the axiom for now. Then you can change theta by the chiral rotation of the quark fields. But now the chiral rotation is not a symmetry anymore, so you end up assigning a phase to the mass terms. And the mass of the quarks goes into the chiral Lagrangian. And then that will tell you how the mass would arise in terms of, for example, mass of the neutron. And the mass of the neutron then acquires a slightly complex contribution to it. And then you have to do a chiral rotation for the neutron field. And the chiral rotation of the neutron field would then turn magnetic dipole moment into an electric dipole moment. And that's how the electric dipole moment gets induced at the end of the day. So every step is well defined, and you can actually do a pretty good estimate of how much neutron electric dipole moment gets induced by that. Does that answer your question, Eric?
Yes, thank you.
Oh, okay, great. All right, so I need to stop here. And so that's the end of the classes and discussion section and everything. So I hope you would work on the homework problems that's still remaining, and I hope you will enjoy that too. And I also am trying to finish up the last lecture notes on topology, which is getting already unruly long, the lecture notes, but I'm trying to put everything I talked about in class, which is beyond the scope of the Peschken-Schroeder book, into the lecture notes, including this stuff on Axion and stuff. So I hope that will be helpful for you too. Okay, so be safe, and hope to see you in person at some point in the future. All right?
Thank you.
Bye. Have a good summer.
Okay,
Thank you,
bye.
Professor. Have a good time.
All right.